In the previous video, we've discussed stochastic non-stationarity, and now let's have a look at another type of non-stationarity called deterministic non-stationarity. And this could be, for example, just a model with a deterministic trend. So if you look at this equation, y is a function of a constant and the time trend. So this is the case. So in this case, y has a deterministic trend, which is represented by this t variable. We can also have deterministic trend with a stationary component. For example, yt is now a function of beta 1, the trend, and beta 3 multiplied by the value of y in the previous period. And the very important aspect of beta 3 is that it is lower than 1. That's why we say that there is a stationary component. Because if beta 3 was equal to 1, then we would no longer have a stationary component. We would have a non-stationary component, and this case will be similar to what we had here when yt was just a function of yt minus 1. But in this case, since beta 3 is below 1, the shocks do not stay in the system, they die away with time. However, the trend is still there, and y is said to be non-stationary around the trend. And we can also have a mixture of deterministic and stochastic non-stationarity. And for example, here we've got the random walk with drift and deterministic trend. So yt is now non-stationary around the trend, and also it is a random walk with drift, because here we've got the drift, the constant value, and the random walk is right here because yt minus 1 enters the equation with the coefficient of 1. So in this case, the shocks do not die out, they stay in the system, and we say that this model has perfect memory and that y is also non-stationary around the trend.